So okay, I will go to the e-learn. Okay, do you see the screen?
Boleh saya?
Okay. Okay, let's look at the subject again, and we are now studying mechanics of material. So what is mechanics of material? It is about some university they call it strength of material. Okay. Some university call it strength of material. Why? Because your study is looking at the stress. So what do? We're looking at the stress. So we study stress of the structure. Study of the stress of the structure. And why we need to study the stress? And because structure and is measured in the term of stress. That's why. Because structure are measured in the term of stress. So that's the reason why we study this. Let me give you some example. Okay, let's see this example. Okay. So why? Because let's see this example. This is aluminum alloy. Okay. Let me open the big one first. You can see this aluminum alloy. You can see the temperature, tensile strength, yield strength, and we just focus on these two. You can see the unit. The unit here is KSI, megapascal, KSI, megapascal. So KSI is kilo pound square inch. Megapascal is mega Newton per square meter. So what is that? That is stress. How do we get that? is by stress is calculated by stress sigma calculated by force over area. Okay, so that's how you get the stress. So first, force is in Newton, or for the imperial unit it is pound. Pound small f force divided by area meter square divided by here divided by area inch square. Inch square. Okay, inch square. So that's why the unit is Newton meter square pound inch square. So that's a unit of stress, and this unit of stress will basically measure the strength of the material. So you have to study the stress of the structure. This is simple structure. We have two beam here. This is rod, this is rectangular. There is a force applied to it. What we need to study? We need to study the stress from this force to this rod into this rectangular beam. So when we have this stress, the stress of this the stress that go through this rectangular beam, the stress go through this rod will be compared with the material strength, the one that I have shown, the table which I have shown earlier. So that's why we call it strength of material or mechanics of material. We want to study the strength of material after we apply the load, whether this material having the strength. So that is a very simple concept. So you don't think hard about this. Just think of what we are studying now is we are calculating the strength of the structure after the load is applied. And that strength is measured in terms of stress. And we compare with the material strength, which also in stress. So there are two things here you need to understand, which is you need to understand there is stress. When load applied to the structure, there is a stress on the structure. The stress will be on the, compared with the strength of the material that make the structure. So far, anyone having problem with understanding?
Yes, sir.
Okay. Now let's look at this. First, what is the most important thing that you need to do in analysis? Okay. Methods of analysis. First, you need to understand the load or force. Because the load in force divided by the area, you get the stress. Second, you need to understand the cross-sectional area. Area of the member. Okay. And then later on, third one, calculate the stress by dividing the force load over the area. So that is 3. You have to remember this. I'll record this, I put it in YouTube and you can follow. So this is the process. First you need to look at the load, then you have to look at the cross-sectional area and then divide the load over the cross-sectional area. You got the stress. Number 4, you compare the calculated stress with the material strength. Okay. Then you calculate the ratio. Calculate the ratio of the calculated stress over the strength. Okay, sorry. You calculate the ratio, which is, we call it factor of safety, by dividing the strength, the material strength, over the calculated stress, or on the other word, we call it apply loads. Apply loads. So anyone can follow this?
Yes, sir.
Okay. Okay. Now let's look at this. Okay. Let's look at the beam here again. So let me just get the beam out. Okay. So what you need to do first, you have to go and remember back your mechanism. Sorry. Okay. You have to set the force into equilibrium. Okay. Based on the applied load. You need to set the force into equilibrium. This is something we have learned, is something we have agreed, which everything should be in equilibrium. So in order to get equilibrium, we have to translate the force here. Okay. So the force here, we have to use the system of okay, convention. You have to set the convention. So force in the direction of to the right. Okay. So this direction is positive. The force in the direction here is positive. Anything opposite direction will be negative. And similarly, when you have the moment, okay, the moment, sorry, the moment in this direction the moment in the direct right direction will be positive. The moment in this direction will be positive. The moment clockwise, okay, moment clockwise, direction is positive. Moment moment anti-clockwise is positive. So the mean the anti-clock is positive. Therefore, we have said here, as we have force down here, we should have force reacted here. We have force reacted over here. We should have also force reacted in this direction, and we have also force reacted, sorry, over this direction. Okay, so this 30 kilonewton will be reacted through this two force system to get it equilibrium. Sorry, it's reverse. My mistake. Okay. The force reacted the other way, because this is the force reacted, the force applied 30 kilonewton is reaction force in opposite direction. Okay. Opposite force in the opposite direction. So, and why we have the force here? Because we have the force as we apply the 30 kilonewton, we also have force along here in this direction. Okay, we also have the force here along this direction. Okay, we have the force along this direction. Okay, so we are building the equilibrium forces over the system. So far, anyone can follow?
Sure.
Yeah.
How can we know the force direction?
Okay, the force direction. Okay, and we have the force downward. It should be reacted force upward. So there will be reacted force here upward. Will be at this point also will be outward. And then we also, you know, as we apply this 30 kilonewton, there's an opposing force to the left, and there's opposing force the other direction. And then we have the counter reaction force to the right and reaction force to the right. Okay.
Okay, sir. Thank you.
Can you follow?
Boleh,
Okay.
sir.
Anyway.
Can.
Okay. Now you have to get the equation of equilibrium. Equation of the equilibrium. Okay. So what I will do, okay. Okay. Okay, we got this. Okay. So we got this. We got this. We call it free body diagram. The diagram that we have here, we call it free body diagram. Because the free body diagram is used, free body diagram or we call it FBD, to set up the equation of equilibrium. So that's why we need this free body diagram. Okay. Then the question, why we need the equation? So that is a question. Why we need that? Okay. Because we need to determine the forces on each members. Two members here. We got rod and we got beam. Okay. Members, which is we have rods and we have rectangular beam. So that's why we need that. Why we need all the forces? Back to the first knowledge that we have earlier. Why we need the forces? Because the force over area will give you stress. The stress we compare with the material strength. And then from there we know whether the beam here are able to carry the 30 kilonewton or not. Any question on that? So how do we set the equilibrium equation? You set by putting all the forces to zero. Force in the force in the x direction here. Okay, force in the x direction here. Okay, 0. So force in the x direction is 0. Set to 0. What do we have? What are forces in the x direction? We have Ix and Cx. Okay. Okay. Before that, you need to label points. This is point A. This is point B. This is point C. Before you start the free body diagram, to identify the point. So the reaction here is Ax. The reaction over here is Cx. So at direction of x, okay, direction of x to the right, horizontal axis, we have Cx, Ax, Cx plus Ax equal to 0. Okay, Ax equal to Cx equal to 0. Okay, Ax plus Cx equal second y direction. So we have reaction Ay plus Cy equal 0. Okay. Ay, Cy equal 0. Okay. Sorry. We have Cy, we have Ay, we also have 30 kilonewton, which is in different direction. Remember, our convention is positive going up. Other than that will be negative. So, negative 30 equal 0. Okay, so those are the forces along the vertical axis. If we have three-dimensional structure, then we have Z. We also have to sum up all the forces on the Z axis to 0. Now, what do we get? Ax plus Cx minus 30, if you solve them, cannot be solved. You only get Ay plus Cy equal 30. Okay. But for the top one, you can solve. You can solve by okay. We can say minus, okay, we can say Ax, sorry. First is Ax is Cx. So you cannot solve as well. So both are hanging, you cannot solve. Yeah. You cannot get any number from this. So that's why we have to use the moment. With moment at where you get moment. Here at C, we got a moment. Because as you pull this 30 kilonewton down, will be reaction over here. Reaction is a moment. Why we got moment? Because moment is equal force time arm. Okay. So here is arm. So moment AC will be what are the forces acting on C? Perpendicular to the C. We have Ax. Ax acting on C. The moment is here. The arm is here. This is the arm. So at C we have moment at C. Again, equilibrium should be 0. And what we get is AX positive. This AX will turn to the anti-clockwise. So AX time 0.6 meter. Okay. 0.6 meter. We also have another moment. Okay, moment here at C. We also have moment at C due to this 30 kilonewton. Since it will act clockwise, it will be minus 30 kilonewton time the arm is 0.8 meter. So this is equal to 0. Okay. Anyone follow? If you solve for AX, okay, now you have AX time 0.6 meter minus 30 kilonewton time 0.8 meter equal 0. You solve it, you get AX times 0.6 meter equal 30 kilonewton is 30 times 1000. So 30,000. Okay. Newton time 0.8 meter. And then AX will be equal 30,000 Newton time 0.8 meter divided by 0.6 meter. So if you cancel this, so cancel divide mm. So you got Newton. So you got AX equal 40,000 Newton equal to 40 kilonewton. Now you have some number. Now we have some number. So AX is 40 kilonewton. So you place the AX into the equation. Remember here we have equation earlier. Force at X, force along the X direction, we have AX plus CX equals 0 earlier. So we know now AX is 40 kilonewton plus CX equals 0. Now we have CX equal minus 40 kilonewton. Okay. Okay. Now we able to get the CX. Now we got member CX 40 kilonewton. Now we leave with you got AX, you got CX, and then you got AX, you got CX. We need CY, we need AY. How do we go about that? So I cannot solve it. So we have to find something how to do it. How to do it? We have to consider other means. We only consider C, A. Now we have to consider action on B. So we have to change. We have been doing forces at C, forces at A. Now we have to look at B for us to be able to solve the AY and CY. Okay. So we have to look at it. We have to go to B. Okay. So you need to consider now moment at B. Moment at B should be 0. Moment at B should be 0. Okay. That is for sure. Anything should be equilibrium means should be 0. So moment at B will be 0. So moment at B is 0. You will say moment at B, point B. Okay. Moment at B equal 0. So what is moment at B? Moment at B will be, okay, moment at B will be, what are the forces will be acting on B? AY, no, because should be forces which having an arm, a distance, arm 90 degrees to the B. AX cannot because AX direct to B. AY, yes. CX, yes. CY, yes. So let's look at AY. AY time AB, AY time 0.8 because this is arm. So AB 0, okay, equal minus AY because AY okay, AY time, just put in the bracket, 0.8 meter. Okay, 0.8 meter. 0.8 meter. Why negative AY? Because AY will be acting B clockwise. Remember our convention positive anti-clockwise, but AY time 0.8 will be clockwise, so negative. If we solve that, AY equal 0. When AY equals 0, remember we have the first equation, CY, AY minus 30. Okay. So we go back to CY plus AY minus 30 kilonewton equal 0. Okay, CY, AY, but 30 is downward is negative. So now we have CX CX is we have calculate above. Okay. Sorry, we have calculate CY. CY is minus 30. Okay. Y is minus 30. So we have CY minus 30. Yeah. We have the equation earlier. Okay, AY CY equal 30. Okay. So here will be AY plus CY equal 30. Now AY is 0. So 0 plus CY equal 30 kilonewton. So CY now equal 30 kilonewton. Now what we understand here is, so what we are trying to understand here, A here is 40. C is 40. CX is CX here is CX here. Okay, CX here is CX. Here is CX. CX here is 40. 40 here. So this force here is 40. Okay. Here is 40. Okay, CX. Now we have CY. CY moving up here. CY here is 30. So we have 40, we have 30. A here is 40. Okay, here is 40. So now we need to solve CB. How do we get this CB? So we need to use theorem Pythagoras. Okay, we need to use theorem Pythagoras to solve the CB. Now we are very clear. This rod here, AB here is 40 kilonewton, but we cannot get this until we resolve it. So what do we get here is, we resolve it. Okay. We resolve this. We have consider this point. This is the point here. 30 up here going up, 40 going this direction. We will get this CB is 50. So now what we have, CB is 50. CB equal 50 kilonewton. This is theorem Pythagoras. Okay. Okay, theorem Pythagoras. Remember, we have okay. Let me do this. BC equal square SQRT of 40 30 square. Okay, I cannot put it here square. So 30 square plus 40 square. Okay. Okay. Which you end up with BC square root of 900 as hold on. So 900 plus, so because 30 square will be 900, 40 square will be 1600. So you end up with BC equal square root of 900, 1625. Okay, 2500, which is E equal 50. Can you follow this?
Yes, sir.
Now what do we have? We have all the forces at all the members. So what we get here by doing this free body diagram, resolving all the forces to the reaction force through the free body diagram, we now having the forces on each AB is 40 kilonewton. BC equal to 50 kilonewton. Now do you see the point why we need to do this? Okay. The rest will be simple. The rest will be simple because what we need to do the rest is to calculate the stress. Calculate the stress on rod BC. Okay. And rectangular beam AB. This is very simple exercise. You need just to calculate tension stress BC equal to 50 kilonewton divided by cross area of the rod. Tension S AB equal 40 divided by sectional area of the rectangular beam. Okay. So far, any questions?
No, sir.
Okay. So let's go and see what we have done. What we have done is we are studying, this is a fundamental mechanics of material or strength of material. What you need to do is we need to find the stress in the structure member. This is structure member. We need to find the stress. Why we need to find the stress? Because the strength of this member is depending on how much stress put in here by the load 30 kilonewton and how much this material can take. So very simple formula, force over area, you get the stress. So what you need to do, you need to find the stress due to the 30 kilonewton on this rod, on this rectangular beam. It compared to what is the material. What is this material? This material you could put as metal, steel, aluminium, wood. You can just use whatever you want based on your design. You can select. However, the most important thing is you need to know from this load what is the stress. Okay, how much this beam, rod, and rectangular section here, the rectangular beam here, and the rod here has experienced the stress. How much they get the stress? How much stress they get due to the load? Then later you can select what will be the best material to accept the stress. This is how things work. So now, what do we need to do? The most important thing here, if you see through the whole exercise, the most difficult part is determining the load. We have to do many steps for you to get the load. Cross-sectional area is very simple. For rod is pi r square. For the cross-sectional rectangular is width times height. The stress is easy, force over cross-sectional area. Compare with the material strength, is easy. You can get the material strength from the table. Just plug whatever material you want to use to design this and compare it what the stress you have calculated at number 3 here. And then you calculate the ratio. The ratio is the margin, how much margin that you have by selecting the material. If you select wood, probably you have lower margin. If you select steel, it's higher because steel is stronger. So that's a point that we need to find in 5. So the most critical situation, the most important, and the most difficult part here is looking at the load. So what I can say here in this analysis, in this subject, we are more focused on determining the load. As you get the load, the rest is very simple. So how to get the load? You have to go back to your static and mechanics knowledge, which is, I think, MIAT, they call it mechanics of solid. So first thing you need to do, you have to develop you have to bring the theory of everything is in equilibrium. Equilibrium means all the forces acting everywhere will be sum up to 0. You need to have balance. Without 0, you're not able to get it balanced. So all the forces here, 30 kilonewton, been placed here. And this 30 kilonewton will be hold on, Okay, now, can you still see the screen?
Yes, sir.
Okay, so the most important thing is you need to get the load. As we go through this exercise, just now, I personally, to me, myself, I can feel it, the difficult part is getting the load. Once you get the load, things very easy. So how to get the load? You have to think everything is equilibrium. That's what we have learned. So that's why for this subject, you have to go back and review your mechanics of solid or static and dynamic, which that will help you to understand this better. First, you need to go back and look at your free body diagram. You need to understand the free body diagram, how to set up the free body diagram. Before that, you need to understand about equilibrium. All the forces will be in equilibrium. So the 30 kilonewton here will be resolved in the system here. We call this a system. We have two beams here, resolved in here to zero. Okay? So the system here will have all zero forces. No doubt that this bracket go to the wall, this one go to the wall will have the load. True, the wall will have the load. However, along the system here will go to zero. All the forces here goes to zero. Everything transferred to the wall. But we are not analyzing the wall. We're analyzing the system here. We're analyzing the rod and the rectangular beam here. Okay. Free body diagram, you have to set up the equation. You have to set up the equation. You have first, before you set up the equation, you have to you have to determine the point of load. Okay, where are the load acting to? Will be one here, B, all the joint here, and also be acted to this point A here, acted to point C here. So what you need to do, you have to establish the equation of equilibrium. What you need, second thing you need to do is you need to establish the convention. The convention is all the forces to the right on the x-axis will be zero. All the forces upward in the y-axis will be zero. The moment into the counterclockwise will be zero. So what you need to do now, you have the reaction force. The 30 kilonewton will give you reacting force AX, will give you the reaction force CX, will give you the reaction force CY, will give you the reaction force AY. So now we have forces in the system which is reacted by 30 kilonewton to C to A. At C we got CX, we got CY, at A we got AX, we got AY. So, and then we establish the equation. If X, all the forces, F is the forces in the X direction to the right is 0, 0, which you have AX and CX. So 0 equal AX plus CX, one equation. And then the Y, all the forces, F is force, Y vertical direction will be 0. 0 equal, we have AY, we have CY. We have 30 Newton downward is minus because the convention is positive upward. Since this is 30 downward, you have minus. So AY plus CY minus 30 equal to 0 again. And then another thing that we need to do to solve the problem, we also take the moment. We take the moment at C. The moment at C, the moment is forces acting 90 degree to the point. So we have at C we have 30. 30. You can see we can have okay. We can draw something here for you to understand. Okay. Okay, these forces here extended here, and the force here acting to this point 90 degrees. So 30 acting 90 degrees. The dimension is 0.08 meter. That is arm. So 30 minus 0.8 at C. We also have moment at A. A, okay, we have, okay, still at C, but we also have force, which is 90 degrees to C. Okay, this is the force 90 degrees to C. So the force is AX times 0.6. So AX times 0.6 is counterclockwise. So AX times 0.6 is positive. But the CX is going clockwise. So that's why 30, sorry, not CX, CX is no force. Okay, sorry. The 30 times 0.8, but the direction will be clockwise is negative. That's why AX minus 0.6, AX times 0.6 minus 30 here, minus 30 times 0.8. So here is a positive moment, and here will be negative moment. And then you saw the equation, you got AX equal to 40 kilonewton. Cannot solve AY and CY. It's hanging there. So the next thing is you have to take a moment at B. So you change, now you have moment at C solved, but now you have to take a moment somewhere else at C, at B. So at B, what we have, what is acting on B? Okay, B, point B here. So AY, because AY is acting 90 degrees to B here. So AY 90 degrees to B is negative because it is clockwise. So and no other forces acting on B. So AY at B, which is minus because it's clockwise. So AY times 0.8. You solve it, AY becomes 0. When AY becomes 0, we can solve this equation. AY becomes 0, CY is 30. So you can solve CY 30. So now you have all the forces. You have AY, which is 0. Okay. AY here is 0. For AX here is 40. And CX is 40. CY is 30. So you have all the forces that you build in the system through the equilibrium free body diagram. You through the equilibrium equation based on free body diagram, you're able to assemble the equation for the forces and solve all the forces, and you're able to get the value for all forces. Now you got 40, you got 30, but what we want is BC. How to get the BC? We have to use the theorem of Pythagoras, which 40, okay, 40 here, okay, 40 square, and here is 30 square. 40 square plus 30 square square root. So that's why we have 50 here. 50 kilonewton along the BC. By having this, now AX is 40. Yeah? So now this beam AX here is a 40. So we have AB, AX will reacted to AB 40, and we have BC 50. From there you can solve the stress. Now you have the load. You have the load divided by the stress, by the cross-section area, you got the stress. Okay. So you got the force AB 40 kilonewton, AB, BC 50. It's very simple now. Force over area. Area is 50 for BC. Area is pi r square. Is a cross-sectional area of a rod. So you calculate, become 314 10 to the 6. 10 to the minus 6 meters square. So the stress at BC is 159 megapascal. But if you use material steel, steel strength is 165. So you have the steel which can carry 165. You apply the load at this point here, which give you the stress only 159 to the rod here, BC. Then you still have margin. The stress is lower than the strength. Then this structure is safe. Can carry the load. Anyone seeing that?
Yes, sir.
Anyone anyone having questions?
Sir, just now,
Mm.
the moment at C,
Mm. At
why do
B.
we
At
C?
B. C. C. Yeah. C. Okay. Here.
Yeah. Why is it moving anti-clockwise?
Okay. You can see here AX. Okay. AX. Yeah. AX. This is a force AX. Remember? See here's AX. The AX will push this one and rotate along C in this direction. So AX time 0.6 rotate at C. Okay, you must remember a rotation at C. The pivotal point at C. Is it clockwise, counterclockwise?
Yes, counter, sir.
Okay. Okay. Then what else at C? 30. 30. The force 30 will be rotating at C. Will rotate in this direction. Will be negative. Clockwise. Now 30 rotating at C. Okay, 30. 30 here. 90 degrees through C, rotating in this direction. So it is clockwise, which is negative. Why plus and minus? Why clockwise, anti-clockwise? You determine. If you change it, also you can get the same result. The convention is something you determine. You set, but you don't mix. If you want to see, if you say positive clockwise, if you say positive is clockwise, okay, now we have anti-clockwise is positive. You want to turn it to positive as clockwise. You also have to change the force system. So the force X will be positive to the left, and the force Y will be positive downward. So this is convention. Okay. Any other questions? So if not, then I will just okay. What else do we have? Okay. Now let's just do the design. Okay. Okay. Now we have done the analysis. So we have done the analysis, which you have chosen. There's two beam here, rod and the rectangular beam made of steel, which is 165 megapascal strength. And your stress is 159. Okay. If you want to choose, say you want to choose this rod and this beam from aluminium. Aluminium only carry 100 megapascal. That is a strength aluminium. Obviously, you will not get this. Obviously, this structure will fail because you apply 159. Aluminium is 100. So it will fail because it is higher than the aluminium strength. What you need to do? You need to, if you want to choose aluminium, still wanted to use aluminium for some reason, you need to change the stress. Okay, you need to change the stress. How you need to change the stress? You need to lower this 159. You need to lower the stress so that the stress will be below 100 megapascal. How to change the stress? You increase the area. As the area here become higher, the stress become lower. So what they did here, you can see this in this example. It's easier just plug in the, just easier to put the force. Force is obviously fixed. You know the area. The stress you know is 100 because you do not want anything to go beyond 100. You can fix the force, you can fix the area, and then you can fix the force, you can fix the stress, which is 100, you can get the area. You can solve for the area. When you solve for the area, you got the diameter. Now the diameter become 25.2 millimeter instead of 20 millimeter. So you can see the area is become higher, the stress become lower, which allow you to use aluminium, which is only 100 megapascal in terms of its strength. So that's how we do things. Remember, as I said earlier, our task is determining the stress in the structure system for each members of the structure. That's first. And then we compare that stress to the strength, which is measured in terms of stress. You can see still here 159 megapascal, aluminium is 100 megapascal. That is a strength of that material. Then anything that you do, you have to design for this structure member to have, if you want to use steel, which is 159, all the members here should have stresses below 159. But if you choose here aluminium, all the stresses in the member here must be less than 100 because we have said 100 is megapascal is the strength of the aluminium. Okay. Anything else? Okay, what I will do, I will stop here. I will throw in you a small quiz, and then you have to do it in your VLE and submit through VLE, and you type in there the answers and how to solve the problem. And depending which is easier for you, you may want to submit your photo image of something you write on paper, or you want to type direct. I don't think type direct is easier. What I would do is I put in the questions in the Eden as a quiz 1, and you write it step by step as I have shown you on the paper. You take a photo and you submit the photo as the answer to the questions. Is it okay?
Okay, sir.
All right. So please use GPEG. Do not use very large photo file for the answer. Only the JPEG, only the image. Otherwise, I have to open to different kind of format, then it will become haywire. Okay, so hopefully you understand. If any one of you do not understand and lost, can't follow this, not very clear to you, please message me, please WhatsApp me, please email me, call me, whatever mean is open for you to ask the question. So thank you and see you next week.
Thank you, sir.
Welcome.
Thank you, sir.
Thank you, sir. Assalamualaikum.
Thank you.
Waalaikumsalam.
Thank you, sir.
Mei, bangun Mei, bangun Mei. Mei, bangun.